We would like to talk about sharing physically based materials between renderers with MDL. My name is Lutz Kettner, so if you see me later around, please don't be shy and contact me and ask me. And, I'm a senior manager with NVIDIA. Actually not from the US. We have an office in Berlin, in Germany, and we are both from Germany, came in yesterday. I'm leading the efforts on the material definition language design and also the IRE rendering team. So we will see renderings from IRE in here. And I have brought with me my colleague Jan.
So I'm Jan Jordan, I'm the product manager of MDL, also from Germany. So after Vlado talked in English, now we raised a little bit. Now we are talking in English with a German accent, so I hope that's the fine for you. Yeah, and Lutz can tell more about what we want to show you.
So these are the few things that we want to talk about today. We want to introduce what this NVIDIA Material Definition Language MDL is about. How we actually match the appearance of a single material within different rendering techniques. How we actually define these materials in the context of physically based rendering and physically based materials. There will be a little section about measured materials, because that's for us and also for others a quite interesting topic that matches well with physically based materials. Talk about what the MDL ecosystem is actually comprised of by now, and want to talk also about how you could potentially become part of that ecosystem. So what is the NVIDIA Material Definition Language, MDL? It's technology developed by NVIDIA Arc to define physically based materials for physically based rendering, independent of rendering algorithms. That's a mouthful. So I'm a bit curious about the audience, how much of these things, how you can really connect to these things at this point. So I'll try to explain this a little bit. NVIDIA, you know NVIDIA, I guess, right? So known for its hardware, for its GPUs, for its novel use in deep learning, for example, right now, self-driving cars. This is the latest things about what we do. Of course, rooted in computer graphics a lot, and we are actually a company in Berlin with our office dedicated to software rendering. So we write software renderers, Mental Ray, for example, and iRay, and so that's where we come from. So, and this office had then, as a local division, its own company name for Germany. It was Advanced Rendering Center. This is what this acronym ARC means in here. So the Advanced Rendering Center that's located in Berlin. We are from there. Now, physically based materials. Who has heard this term before? Okay. Who's actually knowledgeable about rendering? Who's working or has heard about rendering algorithms? Yeah, that's a good number. We talk about physically based rendering. So usually it's associated with ray tracing or path tracing, more advanced rendering algorithms, things that V-Ray, VRT are doing. Key to that is actually that from what people did in the early ages in computer graphics to just use a floating point value of 111 for the color white, for the light source, and for the material, multiply this together, and then you get a pixel value of white. The change for physically based rendering is that you actually associate physically units to these different entities, and you have to be a bit more careful about the light transport simulation, like linear square fall off over the distance of the energy of the light, energy, and so forth. Then you end up with physically based rendering if you actually respect the energies and the physical units in these things. What goes together with that is that you need to be respectful of a few physical laws to make the rendering algorithms behave correctly. So you cannot just put in a multiplier on a material that enhances the material, that makes it brighter than what the incoming energy would be, because that would make it glow, so that you would add energy by that. And if you have algorithms that deal with indirect illumination, if you have actually things nearby and light starts bouncing around, you start adding energy all over the place, again and again. So that becomes highly non-physical if you would do things like that. So physically based rendering has implications for the materials that they have to be respectful of certain laws of physics, like not creating energy. They also should be symmetric, in the sense that you can actually reverse the directions and you get the same behavior of the material. That's helpful for algorithms that work either from the camera or from the light source and simulate stuff. And there's a few more things. So I think I could be helpful for some of you with this kind of explanation to connect these things from rendering and where we are here with physically based rendering. Now, when it comes to materials, what do we consider materials? How do they look like? I have a few images as a teaser. What kind of materials and quality of materials that we are after with the material definition language that we want to accomplish with this language. So here are a few sample swatches. You have things with textures on it, like the marble up there. You have these tiles, the brick pattern. You have also polished things. You have anisotropic metals here, brushed metals. You have carbon fiber in there. You have translucent materials, transparent materials, and many more. Of course, you have to have cars. We are a bit tired of cars, but you have to have cars. The challenging part is the car paint, typically. So that can be quite demanding to get flakes in there, to get the right behavior of these things. Some other car. Interior shots with various materials, marble, granite, flooring, ceilings, panels. Again, cars. Interiors of cars are actually quite interesting in terms of materials and the variety of materials that the designers use there, and the demand and quality, how they want to visualize these things in different lighting settings. Watches, different metals, lightings in there, jewelry in general, so some gems, gold, silver. Not car. Harley-Davidson has actually quite demanding requests for the look of their paint. They look at some of the car paints as, no, such a paint job we wouldn't do for our bikes. They actually go a bit further. Not sure if you can see that. There's actually the flakes are quite visible over here. It's not noise, it's flakes. Again, a bit of jewelry with diamonds. Diffractions in there. The color shifts, the caustics. So these are all things that come out of the material that you want to embed the parameters on the material that this behaves the correct way so that you can simulate these things with the correct color shifts. Potentially becoming also spectral, with spectral rendering with these things. Some plastics, rubber, plastics with the right diffuse look for that. A few more samples of metals, tiles, woods, various kinds of woods with and without polish. Cloth, various kinds of cloth with its intricate reflection patterns, retroreflectivity and transparency and translucency. A little still life with transparent objects and also cloth in it. Now, that brings me to the understanding of, okay, what does it mean to be independent of the algorithms? Where are we right now in terms of rendering? And this is a depiction of the different render modes in iRay. I want to use them as an example here. There's, of course, also V-Ray and V-Ray RT that could be seen in this universe. And Vlado, next time I want to have an image with MDL renderings from V-Ray that we can show in these slides set up in front there. So we have 3 different render modes to illustrate the point of the independence of rendering algorithm. On the left, it would be a real-time renderer, typically an OpenGL rasterizer or whatever API you use for that. It can run at real-time speeds, 60 FPS and higher. It can create a quite decent look, but there are things it cannot simulate typically, or only with extreme cost and pre-processing. Then there would be a conventional ray tracer, something like V-Ray, Mental Ray. This one is running on the GPU. It's a conventional ray tracer. Witted style ray tracer, a bit more complicated, can do approximations. It doesn't do the perfect light simulation. It can do some shortcuts, can be faster. With that, reaches into the interactive frame rates of 20 FPS, or it can actually create quite nice final renderings in the minutes, or actually in the seconds here. That was the 2 FPS there. Then can even run longer for better stuff if necessary. And then there is iRay photoreal, which is a path tracer with multiple techniques in there, to create really kind of reference image of light simulation for these kind of scenes. So this would be technologically similar to V-Ray-RT as a path tracer to create the kind of results there. Now, they use very different algorithms underneath to really render these things, to do the light simulation. What is standard for a long time is that you can share the scene among different renderers, among different DCCs for the geometry part of side things. What doesn't exist is an exchange format for materials. So you usually cannot transport one material from one algorithm to another renderer, to another application. That doesn't exist. It's actually not that easy either. We set out to define such a thing and work on this. So when we go from a rasterizer up to a path tracer, including ray tracers, conventional ray tracers in between, we started looking at these things and we were able to implement this. And I can show you a few images, and then I start discussing the technology behind this, how we accomplished this. So just to make the point how close these looks of the materials are, irrespectively of the light simulation part that is obviously different in these different render modes. This one is rendered with the OpenGL rasterizer. This one is rendered with the conventional ray tracer, just the direct illumination part in this case. So you can tweak this a little bit, but this is then just the direct illumination part from the image-based lighting here. Going a bit back and forth quickly to show you the differences there. Now, this is then the blend into the path tracer. So this does the complete indirect illumination as well. Going back and forth again. And this would be a split screen. So there you can see side by side that actually things like the car paint and also the blends in glass sometimes, and here's the plastic there in the back for the cover, for the roof, how close they actually look. So that's the idea. Even though the rendering algorithm understandably simulates things differently, you're used to understand these things that are different there. The materials underneath, they look the same. They look like you can really match from one render mode to the other. This was the material that I was working with. You can even edit it maybe in one mode and use it then in the other mode. Now, when we set out to do this, we looked at traditional shading languages and what they are used for. What do you program in these shading languages? Now, what are shading languages? There are basically two kinds. One that you use to program a GPU, GLSL, HLSL, CGFX, and others. So really to program the GPU, individual shader, fragment shader, vertex shader, and so forth. They're actually programming languages. They have some access to dedicated hardware, but they're in general just general purpose programming languages. Then running on the GPU, highly parallel. And connected in these pipelines with the fixed function units to make everything work out there. There are this other kind of program of shading language. They're used to actually make production renderers, final frame renderers, programmable. For Mental Ray, this was a C, C++ API. For RenderMan, for example, it was the RenderMan shading language. And so they were actually targeting ray tracers in this case. There's OSL now, and there's MDL now. Now, when looking at this, what you typically do in traditional shading languages at that time, things like GLSL or the Mental Ray shading language, API in C, C++, there were three things that we saw. One is texturing, which means just texture lookup. So you look up the pixel result, the texel result in an image. We have procedural textures like noises, marble, wood you can do with this. You have transformations of the coordinate spaces that are used for textures, the UV space. You actually move the textures around, you can place them differently, you can program that. You have projectors, so if you don't have UV spaces, you can use a world space or object space projector to do a cylindrical mapping of the texture onto the object, for example. Noise functions, math functions, render state, this is all in this area. That's one part. Then there's another part where you actually define what are the properties of the material that I want to create there. So you move into the semantic and abstract level of materials. You talk about reflections, you talk about glossy reflection or transparency, translucency. So you define things like parameters for those, colors, roughness, and so forth. And then there's a third part, which is very closely related. You start implementing these, and sometimes you might not see the difference a lot in the language where you do both at the same time. So you start actually implementing the glossy reflections. In a rasterizer, this might be a light loop to evaluate all the lights with respect to your glossy reflection. In a ray tracer, you actually start tracing rays, shooting N rays. You do maybe portent sampling and stuff like that. For transparency, for a rasterizer, nowadays you do order-independent transparency algorithms, or in a ray tracer, you just do ray continuation. You just keep going. Looking at this, obviously part 3 is algorithm specific. So if you want to define a material definition language that works across these different things to define your material, you can't do this. You don't want to do this. Otherwise, you end up implementing multiple versions of the same thing in the language. So MDL is really based on the idea we cut out the renderer-specific part, and we are left with a programming language, which is a procedural programming language, a C-like programming language for the texture lookups and all this stuff, and with a declarative material definition, so we don't not longer program this stuff out in terms of procedural functions there, but we just declare that we want to have a glossy reflection with these and these parameters, we want to have a transparency with this and this behavior, and so forth. So to drive this point really home, that part is canceled. We are left with these two parts. We will explain this in more detail what this is. And the point is MDL is not a shading language because of that. What does it mean? MDL defines what to compute, not how to compute it. There is no programmable shading in it, shading in the sense of shading a pixel, that's the terminology in rendering. No light loops or access to illumination. No trace call, no sampling, no camera dependence. Just to mention a few for those who know these things. Now, talking about the second part, the declarative material model, because that's more unknown and more innovative than the other part. The procedural part is pretty straightforward. We will also talk about this a little bit later. The declarative part is, it starts out with a declarative material model, a canonical material model underneath. It's pretty conventional. I'll start introducing this now. So we have one material, that's where we start always with. It's a material. It has then different building blocks, one for the surface, one for the volume behavior, and one for conventional modeling that you do in shaders for geometry. I'll detail this in a second. We also distinguish between the surface, which is the front side of a surface, but we can also do a different material behavior on the back side of the surface. So that's, we have this actually twice, the surface behavior there. Let's talk a little bit about how the surface is composed of. One is we use BSDFs, the bidirectional scattering distribution function, to model the behavior of light interacting with the surface. That's pretty common for all the more modern physically based rendering algorithms that they talk about the BSDFs, since Veach and others has been introduced. So we use BSDFs to model that. We'll talk about this a little bit more later. And we have also the emission property, so the creation of light associated with the surface. So actually each and every surface in MDL can also be used to emit light. We have an EDF there, which is the correspondent emission distribution function for that, and we have a parameter then for the intensity, how bright the light is. For the volume, very similar, we have the volume distribution function. This is actually more commonly known as the phase function typically, but for the naming here and the orthogonality of the scheme, we talk about the volume distribution functions here, very similar to the other distribution functions. And we have scattering coefficient and absorption coefficient to control the behavior in the volume. Geometry are the conventional modeling things you do in shading with geometry, like displacement mapping, cutout opacity, like useful for leaves if you want to model leaves or other things there, and the normal for normal mapping or bump mapping. There are two global parameters because they affect actually more than one of these blocks here. One is the IOR, which is the index of refraction as a material property of the enclosed volume. And we have a thin walled flag, which actually controls whether the material is applied to a surface that encloses a volume, in which case the volume properties and the IOR are meaningful, or whether it's just used to define a membrane where the same thing is on both sides. A typical application of thin-walled would be glass. If you model glass just as a thin surface and not as a volume for windows in a car or in a building, then this is typically done with thin-walled. Now, before we move there, I want to point out the icons here. So the color parameters are indicated there, or the vectors for displacement and normal. And for the EDFs, VDFs, and BDFs, there's actually a stack of things because these are structured elements. They have a kind of tree structure. We can use various things to do with that, and this is something that Jan will explain, how these components for BSDF, EDF, and VDF are actually defined and how this creates a very rich universe of things to model.
Okay. So, like Lutz pointed out earlier, we essentially erased a big part of the functionality of traditional shading languages. That, of course, for many people in first glance, looks like we took away a lot of freedom. But one of our goals was that even though we took out the programming part for light surface interaction out completely, from the creative side, it should be as easy as before, if easier, to create really, really complex and demanding materials. What we did to enable this is essentially that first we moved on to a declarative part, and for the declarations we devised a large vocabulary of basically basic functionalities that could be combined in the material model. The basis for that is bidirectional scattering distribution functions, which in essence means it's a mathematical description of the light surface interaction, detailing what happens if a light particle, photon, hits the surface, what probability it has to go in a certain direction or do a certain interaction with the surface. So at the basis there is, for example, diffuse reflection as one of those interactions, which means that light is just scattered in all directions equally. We have the same thing for transmission, so going through the material, we can define a diffuse transmission, which will look like basically frosted glass, and it means that once a light particle hits the surface, it enters the volume and it's going there in equally probable directions. Then we have glossy, let's maybe go for the specular first. Specular interactions are essentially mirror-like. You have a completely flat, ideal surface, and you have a perfect reflection. So if a light particle hits the surface, the outgoing angle is essentially the mirror of the incoming angle, and you get mirror-like effects, and we have the same for transmission, entering the volume, just getting refracted and continuing the way through the volume. And in between, essentially, there are glossy interactions, so glossy transmission and reflection, which means that if a light particle hits the surface, it will go in a certain direction most of the time, but sometimes deviate in slightly around that angle, and it will give you a blurred reflection in that case. One specialty of MDL is that we have also a BSDF as a measured data blob. So there are scanners out there that can measure the distribution characteristic of light when it hits the surface, and we can also basically use that. In the current release of MDL, we added some specific distribution functions. I don't want to go too deep into those. If you look at them, they're all glossy and they're looking pretty similar. So the question is, why do we have them? This is really if you want to have a very specific effect. If you did a match of a BSDF to a measurement, then you might want to have a specific one here, or if you have specific artistic preferences, then a lot of people nowadays go with a GGX, so we added that. So none of those individual BSDFs can do more than a very simple material. So the diffuse one, it's essentially maybe some plaster or something, but and the glossy, they kind of look like metal. but usually materials are way more complex, and common material models usually combine multiple of those distribution functions to create more complex effects. And we also added that to MDL, so there are first essentially, oh no, one step backward. So like Lutz said before, we also have this for emission and also for volume effects. So those are to complete the full spectrum of distribution functions. So if we want to model a more complex material, then it's not just basically the BSDF. We want to have more. We want to modify the BSDF. Maybe we just want to give it a different color. But there's more complex things. We could do a color fall off with a directional factor or with a measured curve factor, or we could add thin film interference effects on top of a certain BSDF to vary the appearance of the BSDF. And last but not least, we can use combiners to combine multiple distribution functions to create even more complex materials. We have mixing distribution functions, and we have a set of layering functions that can be used to kind of layer multiple BSDFs on top of each other. In the right example, it's essentially a specular reflection layered on top of a diffuse reflection, which in the end gives you a dielectric, so a material that is basically plastic-like or something like that. So, and like Lutz pointed out in the slide, this is a whole stack, so it's not just combining two together to create one more. Now you can basically recursively add more complexity to the equation. So one more complex example in practice would be kind of a layered car paint without flakes in this case that has multiple effects. We could start with a diffuse red reflection, but we might want to add some color shift at the edges. So we could do a custom curve layering of a yellow one, and then you would see that the diffuse effect would change to more yellowish at the edges. We might maybe have some coating on top of it. We could add that with a glossiness. Here, with a glossy layer, the roughness of that one is relatively high, so the highlight is broad and soft. There might be a secondary highlight that's sharper. We can add that too. And last but not least, we could cover that paint with a clear coat and have some really complex material built out of simple building blocks. Okay, so far this was all pretty abstract. The event is essentially called Code for Art, so maybe we should actually look at how this looks in code. It's also not too hard, so I guess all of you know how to code. Anybody having no idea about what programming code looks like? No hands. Cool. Okay, maybe it will be a bit too easy. So, Lutz showed before that the basis of this is kind of a material model that puts together certain aspects of the material. MDL, in its essence, is a C-like language, and we use C-like language constructs to basically put things together. Our basic model for modeling this is a simple C struct. This is the basic representation of a material, and you might recognize some of the fields there from the diagram that Lutz showed before. So there's a surface and a backface, and there's an IOR, and there's volume and geometry. And those subfields sometimes are basically structs themselves. So the surface contains the BSDF, and another struct that is the emission. So this basically hierarchical construct of structs is what we use to represent the material. We added something to that compared to what you have in traditional C. So in our world, structs have basically default values. So if you instantiate that struct, basically there will always be a default for all of these fields already generated. So the default material will not be thin-walled, will have a IOR of 1, and it will have some basic characteristics already applied. So if you now instantiate this material, you will have it fully defined, so you can actually render that without doing anything. So of course it will not be pretty, because essentially it's the neutral form, so there will be no reflection, no volume interaction, no emission. It's just black. So, but it works. So the real value of that you will see hopefully later. You don't want to basically just instantiate that. You actually want to create new materials that users can configure to their own liking. So what you typically do is you create a new material that has a set of parameters, and it should have a certain look. So you not instantiate the default material, but give it some arguments so to configure how it should actually look like. Again, if we don't do this without specifying anything, we get the black one. But now we have my material, which is black. Really interesting, it becomes, of course, only if you start filling this in with values. So this is essentially the most basic, useful material that you can generate. So here we specify a different surface interaction for that one, and we say that the scattering interaction at the surface level with the light should be a diffuse scattering, reflective scattering. So and what you get is, in that case, a white diffuse reflective surface, which already probably looks like some materials that you know from reality. In fact, it's not really realistic because it's 100% reflective, which no real material is. So we want to configure that further, and we want to allow our users to basically specify the color of that material. So my first really useful material I call plaster, and I give it about 70% gray reflectivity as a color, and otherwise it looks the same. And now I have really a new material that I can use in my rendering, which makes sense. So defining basic materials is pretty easy. Because of the default values, you always get something that makes sense to the renderer. So it's never, what we try to achieve is that the renderer never has to guess what to do with this material. The material is always fully specified. So so there's very little room for interpretation at the renderer side. Of course, you can also create more complex ones. So in this case, the scattering distribution function is not just a simple diffuse. It's essentially a Fresnel layer of a simple glossy BSDF onto a diffuse one. The glossy one is white with a certain roughness. And the diffuse one is having a custom color. And with this one, I get plastic. Most of the dielectrics and plastics have IORs at around 1.5. So if I just put in the right physical values, I get a physical plausible and already pretty realistic looking material without having to know too much about how this is rendered in the end. Of course, you can get further. If anybody is basically interested in knowing more about how this actually works, we are working on essentially teaching material for how to create complex materials in MDL. You can find that at mdlhandbook.com. One of the examples we have there is, for example, this silk material, which combines 4 glossy lobes with different anisotropy direction to mimic some of the behaviors of silk with different colored threads together to get the final look. And if you look closely, then it's not too easy to see on that projector. Then you can see that there are different directions of highlights, and some of the highlights are actually more on the purple side, and that's how this kind of fabrics actually works. And it's essentially based on a paper on fabric BSDF, which implemented a fixed BSDF, and I just basically wanted to show how you can transfer even such papers onto MDL and mimic the look that is given in those papers. So this is the declarative part. So even though you can't really program the light surface interaction, you can really cover a huge area of materials with that. But all of the materials I showed so far, they don't have any variation on the surface, so they don't have any texturing. For the texturing side, we have also a C-like language. Both parts are not separate. They are actually written in one code base. But here, you can do full programming. Compared to traditional shading languages, though, the state is, or the amount of information, which is usually transferred to something that's called state, is smaller than in traditional shading languages, so you can't do reactions directly on light sources or camera or on the geometry, but you can do spatial variations based on quite a cool state that you still have. In geometry you can, yeah. And what some users of shading languages or graphics APIs or graphics programs are also used to is that sometimes people tend to create complex shading network by combining multiple shading blocks to create complex effects. We have also an equivalent for that in MDL. You can essentially combine multiple, you can essentially create shader graphs, function call graphs that are our form of representing shader graphs. Again, what does that look in practice? Code. So again, it's C-like. So a function definition in MDL is composed of a return value type, a function name, a list of parameters, and in between we have some statements, so that should be pretty straightforward. A very simple function that actually is already pretty useful, just to show you some of the concepts. This is a function that returns a color value, and it creates that color value by looking up the actual texture coordinate at the specific, at the current rendering pixel, and returns that as a color. And this is already pretty useful. If you use that in a material like we used in the plaster before to configure the plaster color, then you can see that the color of the material basically changes based on the position on the object, which is what UV is usually about. And it's already pretty useful as a diagnostic to the user because he can basically figure out if his UV layout makes sense or is good for texturing. So even such a small function basically is already useful. I use this function because it basically illustrates two things. First, it illustrates how information is passed into such a function. So there are not only parameters to the function, I actually have none in this function. Instead, this function accesses some implicit information about the current rendering state by calling a predefined state texture coordinate function, which will return the texture coordinates. The other thing is that what I would like to point out here is that color in MDL is not RGB. The color type in MDL is essentially an abstract data type, so also here we leave it to the actual implementation to define what color is for you. So the return might be an RGB color, and often is, but in some cases, also for example in Iray, it could actually be a spectral value, so essentially a range of intensities over a certain spectrum. So you're not limited to such simple functions. It's a full programming language. You have control flow, loops, switches, conditionals, and you can build fairly get functionalities in MDL in the program in the texturing language. Here, this is essentially a port of classic procedural texturing function from CAN Perlin. It's called some Perlin noise. It essentially calls the basic Perlin noise function, which implementation is more detailed again on the MDLhandbook.com page. At different frequencies, sums them up to create something that looks kind of natural and useful. And if you now use that to basically color your cluster, you already get something that kind of looks marble-like. So yeah, and this is how procedural textures for marble, wood, and so on are constructed. So all this is essentially also possible in MDL. And you can also see that it's not calling just one function, but instead here in the material definition, we have a color constructor that calls the sum Perlin noise function, which in turn acquires the texture coordinate through state function. So what you have here is essentially a function call graph that in a graphical application like Maya or so could be used to graphically put together complex shape graphs out of simple components. So much to what MDL looks like at the syntax level. I would now give over to Lutz to show some of the other uses that we have for MDL.
Thanks, Jan. And you did say that black is not beautiful?
I said that. Black is not a color, sorry.
Good. Coming to measured materials. I think we also have to look a little bit at the time here and step over one or the other thing that we prepared. But I understood we have a little bit leeway, or maybe I'll get for an indication here from the organizers how much time we have.
Okay, 5 minutes.
Yeah, that's good.
Okay, then very quick, I guess.
We'll make it do. Measured materials come in various flavors, various devices, a little bit outdated. There is actually quite some activity right now, including a device from Chaos Group.
Yeah, we do it in the question.
One way of representing measured materials, a common one and quite useful, is the spatially varying SVR-BRDF. So you have a BSDF and you use its input parameters in the measurement process to fit textures that drive these parameters. So you get a set of textures out of the measurement device and you feed them into such a material. So that works very well with MDL. We have various incarnations of where people fitted these things. And this way, actually, these custom or these dedicated, very specific glossy BRDF models came in. If you want to do a measurement, you want to fit the exact BRDF. Otherwise, you have an unknown error that can actually be quite significant in corner cases for the measurement. More advanced devices do things like BTF measurement, bidirectional texturing functions. They are 5-dimensional, they are huge data sets. You start compressing them. One way of compressing them is actually using a fitting also to an SVBRDF representation. This is what you also get out of the X-Rite device, here the tech device. That's something that we can also handle then in MDL, or a similar representation, including a flake layer. Then for that. So this would be a rendering out of a measured AXF. Actually, the towel, this one, the white towel as well, and the basketball, they are actually measurements coming out of the tech device that we render here in MDL. Pointing out an important context why measured materials are of interest also in MDL and how to combine this in MDL is if you measure something like just an isotropic point sample or point BRDF here, not spatially varying, just the point measurement, for example, with the Radian ZMAX imaging sphere, which is the device here in our office that we have actually in our office in Berlin. You get a measurement that looks like this. Because of the measurement process in the device, you have a sensor, you have a light source. They start moving around. They get into each other's way, so there is a kind of blind spot where they can't measure, which has to be filled by other means, algorithmically typically. And if you start moving at the grazing angles, because of the finite size of the sensor and the light source, you have limitations of how far you can go close to the grazing angle. So you actually get too dark grazing angles typically in these kind of devices. Now what you can do is you can, by having this meta-knowledge that this is actually a material that has reflections at grazing angles, this kind of Fresnel effect, you can add this with an MDL component and kind of repair your measurement and add this. Get a nicer look. And then you can become artistically inclined and actually create further effects and use this in an editing process and create, for example, a bump map as a simple case here to make then a nice looking measured and then modified and improved material for a car based on a measurement. Now, a few additional benefits, skip over that one. I skip over light path expressions, I would say, at this point. It's a nice complementary technique to do artistic compositing with frame buffers that helps regaining artistic freedom that you might think is not available anymore with the BSDF model. This is why we have this in here. I'll skip over those. Maybe we should go
one further, I guess.
Bit with the timeline, and then
since we
your
just have a few minutes.
Yeah.
So MDL is not new. We started actually developing this 2011, and we basically had also something before as a first incarnation of something that does shading in a portable way called MetaSL. There might still be something out on in some of the big packages. So it's still out there, but it had its problems. So we basically moved to MDL. At first, of course, for our own uses, but since 2016, essentially other vendors basically announced support. So V-Ray will support MDL. There are some specific renders for specific use cases that use it, and we expect that to grow. So right now, the ecosystem is mostly composed of NVIDIA applications, but you already see V-Ray all in there. But in all of the applications that basically have the thick arrows, you can import and export MDL and therefore move materials from one application to the other. For people who don't want to write code, which are probably not here in the audience, there are also graphical tools to develop complex materials. So Substance Designer is historically a procedural texturing tool, but now they also implemented MDL authoring functionality. So for the graphics artists, it's also pretty close to just generate those effects that I showed earlier without actually writing no line of code. And with this, we essentially want to free the materials from the application and allow users to decide themselves where to author materials, where to use them, and how to consume them.
I'd like to mention quickly for Substance Designer, this was a single material. This was not multiple materials on geometry. This was a single material on each of the strips there.
Yeah, they come from a competition they hold, yes. Right? So to get the ecosystem started, NVIDIA also provides a library of free materials to use and to look into. They can be downloaded from our website. But now for the more important last part of the presentation, I know already there were some questions. How can people basically become part of the ecosystem and use MDL? There was a question on the smartphone whether we have the parser available for free for download. I come to that. So right now you have essentially 3 ways to doing that. You can either basically use an MDL-enabled renderer like V-Ray or I-Ray. Then you can basically write your own compiler. The specification is definitely free available, so anybody can download that and implement the compiler based on that. And then there is basically something we call the MDL SDK, which is essentially not freely available, but this is how, for example, Chaos supports MDL. In detail, the MDL specification can be downloaded from that location. Vlado mentioned earlier that some bad companies sometimes patent stuff, so it makes it hard for others to integrate. In order for you to not worry about patents too much, every possible patent that NVIDIA has that is required to implement the MDL specification is automatically covered. So if you implement the MDL specification, you don't have to worry about us, at least. So in order to help you on request, we also make a synthetic conformance test available that you can download. And yes, at some point we need an open compiler. A parser is essentially only a first start. We actually might do something with the parsing front end also, but there's more needed than a parser to actually do something really useful with MDL. So
maybe to quickly mention that if it's about parsing, there's the grammar in the appendix, so there's a full grammar that comes with that.
Yes.
But of course, that's not enough. I mean, you need more semantic analysis to work with that in the end. Yeah.
So and what we are also working on is basically semantic conformance tests, so not only tests that the syntax is correct, but also that to some extent the result of the material definition is the same across renderers. But this is something we're working on. Then there's the MDL SDK. This is a binary SDK. It is available for licensing, but this is also, I mean, we essentially want to get this in products first, so there's some overhead for us to basically do support here. So if you're interested, you can contact us, and we can basically talk on what we could do there. This SDK does, of course, parsing and resolution of MDL content. It stores the result in an internal database, and you have some editing capabilities that you can do there to create call graphs of shading functions and stuff. And then it has two different compile steps. One is to compile the material into an optimized directed acyclic graph view, which essentially allows you to look at the declarative part of the material and fit that to your rendering algorithm. And then there is a compile functionality for the texturing part, which compiles texturing functions in a linkable form for various backends. So this can output GLSL code or LLVM-IR code based on MDL texturing expressions in the end, and you can use that to link that with your shading code. And then, of course, you have the MDL SDK in use. Those are two basically of the current use cases. Like Lutz said, we want to have more newer renderers from Chaos, from V-Ray. Those are actually from, I think, April or something like that, so it's not too up to date. Yeah, and those are essentially basically examples of integration of MDL using our MDL SDK. And that's basically it. I think we even went over the 5 minutes, but anyway, so we presented what MDL is, how the MDL ecosystem looked like, at least quickly, and then we have something called V-materials to basically get a look at what practical MDL materials look like. And then we covered how you could become part of the ecosystem by either downloading and using the specification, which is free, learning how to code MDL through the MDL Handbook, or basically use the MDL SDK. There are more resources. There's also some sample code for that uses the MDL SDK to create GLSL code for a GLSL renderer freely available. And then there's MDL conformance test suite, and that should be it for the presentation. Any last words from you, Lutz? No? Okay. And here's the link for